Okay, shall we get started again? All right, so now I would like to basically repeat that paradigm in the context of nonlinear optimization. So, and a few other issues will come up, which I'll discuss a little bit. So, here's a nonlinear programming problem. I'm going to minimize some function f, no longer linear, subject to a bunch of inequality constraints, let's say from 1 to m. Okay, so just to be clear here, for linear programming, I always like to maximize. I'm an optimist. But in the nonlinear world and the convex analysis world, it's all about minimizing and convex functions, not concave functions. And so we have to make a little bit of a paradigm shift here and switch to minimization problems. And so that's like the dual. And so rather than having a less than or equal to constraint, it makes more sense to have a greater than or equal to constraint. And when we had the dual problem, I had A transpose something is greater than or equal to a constant vector, C. But in nonlinear, I don't really need to put that C there because I could just subtract the C and put it as part of this general function H. So there's no reason not just to have this be 0. So this is the problem, the basic setup in nonlinear programming. Inequality constraints, a function to minimize. And so I'm going to follow the same basic steps as before. First step was replace inequality constraints with simply non-negative variables by introducing slacks or surpluses. I guess in this case it would make more sense to call them surpluses, but I call them slacks anyway. So that's the first step. The second step is to put those non-negative variables into the objective function as logarithmic barrier terms. So we subtract the sum of the logs of the w sub i's. The next step will be to introduce the Lagrangian. And so we write the objective function minus some Lagrange variables, which will be our dual variables, times the various constraints, e to the x minus w equals 0. Okay, and once you have a Lagrangian, the next step is to take derivatives with respect to all the variables. So if I take derivatives with respect to x, now I'll use gradient notations because it's sort of convenient here. So the gradient with respect to x variables gives me the gradient of f. There's no x's here, so it's gone. And here I get the gradient, well, so now you have to think about it a little bit. This is yi times hi of x summed on I, so it's really just the sum on I of yi times the gradient of hi. But we want the end, when I write this in matrix notation, I want that to be a column vector because my assumptions are always that vectors are column vectors. So my gradient here is a column vector. And so what is the gradient? So this was a vector here, h. This gradient is taking the gradient with respect to the x variables. So this is a matrix here of the derivative with respect to xj of h sub I. So this is like a linearization, and so it's like an aij. It's like an element of the matrix aij. And then if you think about it for a few seconds, to make the dimensions match up, it's the transpose, because the I has to get multiplied by the yi here, and so it's this matrix, this m by n matrix transposed. So that's That's the one set of equations that you get by taking the gradient with respect to x, take the gradient with respect to w, and I think we get basically the same thing we had before. Nothing's changed. Take the gradient with respect to y, and we get essentially the same thing as before again. We get the constraints of our problem, which are now written as h of x minus w equals 0. And we do the same trick of rewriting the system by multiplying, well, let me just emphasize, go back, by multiplying through by capital W here. And get this system. There are no xz parts here for a reason. The reason there's no x times z is because x in this paradigm is a free variable. If x is a free variable, it's not necessarily greater than or equal to 0. That means on the dual, if we were doing linear programming, that would mean on the dual side there would be no dual slack. The dual constraints would be equality constraints. So if this were linear programming, with x free would give me equality constraints on the dual. There would be no z. There would be no complementarity conditions. So it's quite natural that we have no z to introduce here like I did before. Okay? And we apply Newton's method, like I was saying before, to compute the search directions, delta x, delta w, and delta y. And we get that just by linearizing the system of equations. Newton's method is the next level of derivative times your step directions equals your current thing. So here I write down what the next level of derivatives is. So I'm taking the derivative of this thing here. The gradient of x becomes the Hessian matrix, the matrix of second derivatives. So derivative of f with respect to xi and xj, that appears, and I get the Hessian of each of the constraint functions h sub I, add it all up. So I get this linear sum weighted by the dual variables, or the Lagrange multipliers, whatever you want to call them, the Hessians of all the h sub i's, and that's what appears in Newton's method here. And there is no w in this thing, so when I take the next higher derivative, nothing appears here, and and when I differentiate with respect to y, I just get an A transpose. And I get, there's an extra minus sign in Newton's method somewhere. I guess it's over here. So that's why there appears to be a sign difference between what's there and what's here. And then the second row, I have to take further derivatives of this thing. So it's derivative with respect to w is y, and the derivative with respect to y is w, ignoring the extra minus sign. And so I have a y times w and a y times delta w and a w times delta y. That's what I get for the middle constraint. And the last one is the derivative of this thing, which again, the gradient of this h is what I'm calling, oh, I didn't say that. What I'm calling A here is this matrix of the derivative of hi with respect to xj. I call it A because it's exactly like the A of linear programming. It's the linearization of the nonlinear constraints. That's exactly the linearization of the nonlinear constraints. But now it depends on x because it's nonlinear. So when I take the second derivative, this becomes A, and the w becomes an I, and there's an extra, the minus sign. There's a minus sign in front of here that we have to ignore. So, so this is just Newton's method to get the step directions. And we get this system of equations, and we just have to solve them. And in a sense, everything is done. We solve for delta x. We solve the system of equations. We've linearized. We would like to take a step in that direction. We will shorten it if we need to keep the things that are non-negative to keep them non-negative. That would be the w's and the y's. We don't care about the x now. The x can go negative. And it's important to point out that sometimes this matrix H is positive semi-definite, and sometimes it's not. It is positive semi-definite if F is a convex and if each of the H's are concave. So then this is just the Hessian matrix of a convex function, and because of the minus sign, this is also convex. And the yi's are non-negative. So everything, so this becomes positive semi-definite. Okay, so that's going to play a role. And again, using the same idea that I did before, let me back up, emphasize this. We want to simplify this a little bit by solving the easy part of it explicitly and getting a slightly smaller system of equations to look at. And I'm going to do the same thing I did before and look at this sort of mu complementarity linearization equation, this middle one, and use it to eliminate W, I believe is what I'm going to eliminate. So I eliminated W and only have delta x, delta y left, and now the whole system of equation looks like that, which is similar to what I had before. I had A transpose, I had W, Y inverse, you can almost still read it. And up here, I had something positive definite. Oh, there's a minus sign missing. Oh, I have the minus sign here. That's probably because of the difference between minimum and maximum or something. Yes, there has to be, one of these has to be positive and the other has to be negative. I've actually introduced the term quasi-definite system for a system of equations that can be written in block form like this with a matrix, the transpose of a matrix, and a positive semi-definite here and a negative semi-definite there, or vice versa. And it turns out that that's better than these being both positive semi-definite. That's actually a harder system to solve. Okay, so we solve this reduced KKT system, and we shorten our step lengths as necessary, and we update to a new point, and we just iterate, and everything is the same, basically. Almost.
Sorry, the complexity is a necessary condition? Because if not, with a step you could go out of the complex rule.
So, interior point methods for convex problems find the globally optimal solutions. I'm going to tell you in a few slides about some changes to make to the algorithm which will encourage it to find at least a locally optimal solution when the problem's not convex. But when it's not convex, now it's difficult. But I think the algorithms that exist are fairly reliable at finding a feasible solution if one exists. I mean, of course, that's also hard. And the fact that that's probably the hardest part. And then once you find it, finding a locally optimal solution. But what does local mean? There's no proof that this is the closest solution, the closest locally optimal solution to the point you started at. So it's all just trying to find a solution which might be close to the one you started at. Okay. I don't remember if I have a slide here that elaborates on this quasi-definite property. But so let me finish what I have here, and if there's time, I'll mention why having one of these positive definite and the other one negative definite is better than having both of them positive. Okay. Oh, so it's the next slide here about convex versus non-convex. So, so if we extend our class of standard problems to include some with equalities and some with inequalities, a problem is convex if whenever you have equalities, it has to be an affine function. In other words, linear function with and then some right-hand side that doesn't have to be 0. So just linear constraints. If it's equality, they have to be linear. If you have inequalities, and we write them as greater or equal to's, and the functions h sub i's have to be concave functions. And if we're minimizing, the function f has to be convex. So it's a convex nonlinear programming problem if you have these conditions. And we'll call it smooth if all the functions that we see are twice continuously differentiable. So if we're in that situation, that's the convex situation, that's almost as good as linear programming, but it's not quite as simple. There's at least one other subtlety that I have to mention. Actually, quadratic is still okay, but you have to actually go non-quadratic, but still convex before this subtlety appears. It does not suffice to choose the step length simply to keep you from going negative. And here's a trivial example to illustrate this simple point. Consider minimizing this function. Don't even have any constraints. No constraints. The variable x is a free variable. It can go positive or negative. And the iterates of the interior point method, which in this case are just exactly Newton's method, do exactly what's shown there. And I can maybe sneak a little picture in here of what's happening. This function here, the square root of 1 plus x squared, what does it look like? It's 1 when x equals 0. It's 1. And as x goes to infinity, that 1 becomes irrelevant. It's asymptotic to x, and it's asymptotic to minus x as you go to minus infinity. So it's a very fun function. I like it very much. Anyway, if you write down what the interior point method would do for this, it would do exactly what Newton's method does, because there's none of the other none of the other complications of nonlinear programming. And Newton's method approximates this function with the best quadratic function to approximate it. So if I start way out here, this is almost a linear function. The best quadratic approximation to this almost linear function looks like this. And then I find the minimum of it, which is way over here, which now I take that as my next point. And so now I take the best quadratic approximation to the original function here, where it's even closer to a linear function. And now I do that quadratic approximation, and its minimum is way over here. And that gets worse and worse when I'm far away from the optimal solution, which is x equals 0. And in fact, if you look at the iterates, that's telling you exactly that's what happens. The next iterate is the negative of the cube of the current iterate. So if I start at 2, the next one will be at minus 8, and I can't even cube minus 8 in my head. The next one will be at 8 cubed. So it grows fast. But if x starts out less than 1, then that converges to 0 extraordinarily fast. And so, of course, there's a huge body of research on Newton's method and when it converges and superlinear convergence of it, and so on and so forth. And all of that research is a special case of interior point methods. And so it doesn't always converge. This only converges if x is less than or equal to 1. Now, you can make Newton's method converge by not being so bold as to taking a full step, but shortening the step. And so you have to try to do something like that. So one of the things that some people have implemented is a filter type method to help guide the choice of the step length. And let me try to briefly give some hints as to what this is about. So we end up with this Hessian matrix plus A transpose W inverse YA. Well, I guess you can see that when I solved these equations, at least one of the ways, I got something very much like this. This, let's see, one of these was my Hessian matrix. This was my Hessian matrix. So x z inverse is my, so I've done it the other way. I did the dual. This is done by the dual of that. Oh, I guess that's why I call it the dual normal matrix, because I did the dual of it. Anyway, you saw over there that I got something that looks like this. If you go in the other direction and solve for the other variable first, delta x instead of delta y here, you'll get a matrix that looks like this, multiplying your system of equations. You get an A transpose times A with a diagonal matrix in the middle, plus the piece that was up here, or wherever it was. Yeah, it was up here, H, the Hessian matrix. And so that's the matrix that you have to invert to get your delta x's in this case, because it's the dual part. And so this is the matrix that determines everything. And if this is positive definite, then it has a unique inverse, and you can just calculate your delta x and then your delta y and your delta w. So let's see what does this theorem say exactly. Suppose that this matrix is positive definite. If the current solution is primal infeasible, then delta x, delta w, the step direction on the primal side, is a descent direction for the infeasibility vector. For the measure of infeasibility, the norm of h of x minus w. And so, if we're infeasible, and this is positive definite, then one step improves the situation with respect to feasibility. If the current solution is feasible, then delta x, delta w is a descent direction for the barrier function. That's the objective function with the barrier terms added in. And as mu gets small, that becomes close to the objective function. So when we're infeasible, things improve with every iteration. The infeasibility gets smaller with every iteration. Once we get feasible, the barrier function gets better with every iteration. And if we decrease mu at every iteration, the barrier function gets closer and closer to the actual objective function. And this says it will all work. But it always says it's a descent direction. That means initially, for a small enough step, it will work. So now you have to do a little line search to figure out how big of a step length you can take that still maintains that you had these properties. So for linear programming, it was a descent direction, and it continued to be a descent direction because it was linear. There was no curvature to it, and if it was going down, it was always going down. Here, it's only initially good, and so you have to do a little line search to figure out how far you could go before things start to go bad. So you have to take shorter steps. That's for convex optimization. If it's non-convex, there's more to worry about. If that Hessian matrix is not positive semi-definite, that's basically the definition of being non-convex, because the Hessian matrix was this H matrix was the Hessian of the objective function minus the sum of yi times the Hessian of each of the constraint functions. And so, if the thing is non-convex, then one of those things is not positive semi-definite, and so this might fail. Am I messing up my notations? Hold on a second. Let me go back to refresh my own memory what H is. Yes, I said it right. So H is this. And if it's not positive, if the problem is not convex, then something here is not positive semi-definite. And so if H is not positive semi-definite, then that normal matrix N, the dual normal matrix, might fail to be positive definite. It might not, but it might. There's two pieces to it. This here is positive semi-definite. That's always positive semi-definite. I guess that's an important point. A transpose times D times A is always positive semi-definite. The way to see it is to multiply by any vector, call it C, and on the left multiply by C transpose. This is how you check positive semi-definiteness. And this matrix D is a diagonal matrix with all non-negative entries, so I can take and write it as 1/2 D to the 1/2 squared. And so this is, now all this can be factored, and this is basically D to the 1/2 times A times C times the transpose of that. So this is the norm of this vector squared is equal to this. And so this is greater than or equal to 0. And so so the matrix A transpose times the diagonal of positive entries times A is always positive semi-definite. So this matrix that's being added on is positive semi-definite. So the Hessians here, this linear combination of the Hessians, this might not be positive definite, but that might not be a problem because you've also got these terms here helping you out. And so sometimes a non-convex problem is okay, you know, but you have to worry about when it's not okay. All right. So what are we going to do if it's not okay? If the normal dual matrix is, if the dual normal matrix is not positive semi-definite, then we lose the conditions, the conclusions of the previous theorem. And so we don't have descent directions. So when we're infeasible, it's not going to improve. Or if we got feasible because we were lucky, we won't necessarily get close to optimality because it's no longer going in the right direction. That's really bad. But you can regain those properties of having at least going in the right direction, descent properties, in a very simple manner. All you have to do is perturb the Hessian with a diagonal perturbation lambda. And if you can come up with a scheme for estimating a good lambda, then you're get the descent properties back again easily. And so you perturb that H with this lambda, you replace H with H, this H tilde in the computation of step directions, and you can show that you have all the properties of descent that you needed. And so, just to be precise, if we let n tilde denote the dual normal matrix associated with H tilde instead of the one associated with H, then we have the same kind of result as we had before. If this perturbed dual normal matrix is positive definite, then the step directions are descent direction for the primal infeasibility. And, the theorem's slightly different actually, and for the non-complementarity. So the deviation from complementarity is measured W transpose Y. So the second statement is a little bit different from before. It's not the barrier function going in the right direction, but it's this going in the right direction. But duality theory tells us if we're feasible and we have no complementarity, then we're optimal. And it turns out that in this case, that's exactly what you need. So having these things going in the right direction. Oh no, I'm sorry. I forgot one thing. My mistake. We also have to have dual feasibility, and we don't necessarily get step direction improvement in the dual infeasibility automatically. And so we have to do a line search to find a value of lambda that's within a factor. So what we do is a line search to find a value of lambda within a factor of 2 of the smallest permissible perturbation, because you don't want to. Obviously you have a big lambda times the identity and make it positive semi-definite, but then you've distorted it too much and things will converge slowly. Okay, well if that wasn't bad enough, even more things can go wrong in non-convex optimization. So if the problem is convex and the current solution is not optimal, and some other conditions which are technical and don't feel like saying, then any slack variable, say Wi, then for any slack variable, say wi, if wi is equal to 0, then the step direction is greater than or equal to 0. In other words, it's pushing back inwards into the interior. So for convex problems, as slack variables get small, they tend to get large again. This is an anti-jamming theorem. Maybe I should draw a little picture of that as well. Even for linear programming, it's basically the same picture I drew before. In fact, I can use this picture. The first step goes toward the direction of optimality, but not exactly toward the optimal vertex. It just goes in that general direction. And then we stop short of this wall, and the next time we stop short of the wall. And we're never pointing exactly at the vertex. We're always hitting a wall somewhere. And I drew it to curve around like this because that's exactly how the interior point methods work, is that as you get, for linear programming, as you get close to an edge, the step direction becomes parallel to the edge. But for strict convex problems, you actually push away from the edge. And so this gives us sort of an automatic anti-jamming. But an example of Vector and Beagler shows that for non-convex problems, jamming can really occur. And I guess it's sort of easy to say why. You know, if it's convex, the convexity actually this is for linear, which is the border between convex and non-convex. And as we got closer and closer to an edge, we became parallel to it. For convex problems, it actually pushes us away, and it would have a tendency to step us back into the interior, which in a way helps the convergence. But if it's non-convex, you can actually get very close to the wall, to the edge here, and the step direction is still pushing you strictly into that wall. And so you can jam up against a wall, and you can produce a convergent sequence that converges to the face of a wall, and it never gets to an optimal solution. And so that's a problem that you have to worry about. And so one of the changes I made to my code anyway is if a slack variable gets small, its component of the step direction contributes to making a very short step. So what we do is we increase the slack variable to the average size of the variables of the other slack variables. So we just change it. And we don't have to follow the path. We're allowed to push ourselves back in, basically. So this kind of trivial modification at least corrects the standard collection of jamming problems that people have played with. But there's no theorem here. It's just empirical evidence that it works pretty well. Okay. Well, let's see. I showed you my code, a printout of the run of my code that indicated that my code handles problems that have bounds on the variables, ranges on the constraints, free variables. These things are all treated implicitly. So in other words, I modify the algorithm to accommodate those things as they are rather than reformulating a problem into a standard form. And when you take into account all those things implicitly, you still get to the same kind of equation as we had before. It's just that these diagonal matrix here and here come out to be a little bit different than the simple things they were before XZ inverse and YW inverse. But otherwise, everything looks the same. Anyway, more detail on all these things that are in my book. I wanted just to end for the last few minutes to tell you that I showed you at least one, maybe two, I forget, ample models. I think it's a nice language. There's only a couple languages for optimization. Ample is one, GAMS is another, maybe there's one or two others. And of course there are interfaces for optimization within Microsoft Excel, within MATLAB. but those, I would consider those languages for optimization. You know, if you just have a linear programming problem, you just want to make an A matrix, MATLAB is a fine way to go at it. But if you're trying to write down nonlinear constraints, and you have to actually provide to the software not only the evaluation of a function, but also its first derivative and its gradients and its Hessians. So you need to be able to calculate first and second derivatives of your objective function and all the functions that appear in the constraints. And so I don't think there's a MATLAB thing that does automatic differentiation. But AMPL, that's the contribution of a language like AMPL, is it allows you to write formulas, and it knows how to take the first and second derivative of your things. And so it passes to the solver not only function evaluations, but also gradients and Hessians. And so one can implement this algorithm quite nicely. You can either buy the book that describes it, or there's various websites with tutorials. And these are just a few that I wrote down for my class at Princeton. But I got that short list there by just Googling AMPL tutorial, and there's many, many more. So AMPL is nice. And not only that, you can even run these problems that you write in AMPL without having to buy either AMPL or any solver, because there's a free solver. I think it used to be at Argonne National Lab, but I think it moved to the University of Wisconsin. But anyway, it's funded by the government. It's free for anybody, I think, in the world. It's called the Network Enabled Optimization Server. It's that website that I wrote right there. And if you go to that website, am I online? I think we're probably not online here. Are we online? Maybe not. Anyway, if you go to that website, it's very easy. It has an interface where you have your model, you upload it, you can select one of probably 50 different solver engines. The engine that I wrote is called Loco, so I'm always advocating mine, but there's lots of different solvers, and they're categorized. So there's non-linearly constrained optimization, that one's where mine's categorized. There's solvers that are just linear programming, there's solvers for integer programming, and mixed integer programming, and mixed non-linear integer programming. And there's probably 50 different solvers categorized into probably 6 or 7 different generic categories. You select the appropriate category, you pick the solver you want, you upload your model, and then you give your email address so it knows where to send you the result, and you click submit, and you just wait. And often you only, if you're making just test problems, you only wait a minute or two, and you get an email message with the answer. So it's a very nice tool. Okay. I have 1 minute left, but I don't have anything else to say, so if there's any questions. Well, maybe what I could do is I could show you that little quasi-definite matrix thing, if I can erase that. Yikes, did I ruin this board? So if we just have a matrix that's, I don't know, let's call it D and E and A transpose times something like delta X, delta Y equals something. And how did I write this before? I used the first equation to eliminate delta X. So delta X is equal to the right-hand side, which maybe call it sigma minus A transpose delta Y times D inverse, right? Something like that, I believe. Then if I substitute that into the second equation, I get A times D inverse times sigma minus A transpose Y plus E times Y, delta Y, oh, there's a delta Y here too, should be equal to something, say rho. So now if I look at the delta Y parts, I have A D inverse A transpose plus E all times delta Y equals some stuff on the right-hand side. Now wait a minute. I have a minus sign that's missing right here. This is the important thing. This has a plus sign and this has a minus sign. If I would like this to be a definite system, say a positive definite, I could assume that E is positive definite, but I have a minus sign here, so I want this to be negative definite, so I would like the D inverse to be negative, not a positive matrix. So I would like them to be the opposite of each other because of this minus sign here. If both of these are positive semi-definite, then I've got the difference of two positive semi-definite matrices, and I can't say anything definite about them. That's why this quasi-definite, where one of these is positive and the other is negative, is much better. Okay, so I've used my 1 minute. So thank you.
So it's a coffee break now, and then after the coffee break, I'm going to